Hi, good afternoon, everyone. Welcome to the last session of this workshop. This session will cover the large eddy simulation, right? Yesterday in the introduction session, we understand what are the scales associated with the turbulence, right? So if up we are resolving up to the smallest scale, then those kind of simulation is called DNS, right? And usually it is quite expensive. The computation takes a long time, and for engineering calculation, it's not feasible, right? So we have to cut off at some particular scale, and it is above some particular scale. We have take consider for the simulation. Those kind of simulation is called large eddy simulation. So in this session, we will see details about the large eddy simulation and how they are implemented in a commercial solver, right? So now let's come. So this is my turbulence spectrum, right? Instead of capturing the entire spectrum, right? So I will go up to a particular eddy length scale. This is a wave number. So 1 by the reciprocal of it, it gives the eddy length, right? Up to a particular wavelength, I will go there and I will cut it. So means the smallest scale eddy, I am not taking into consideration. Any eddy size greater than that, I am taking into consideration, right? So if you look at the picture, yesterday I showed about the turbulence cascading. Eddies of different size superimposed over each other. In the turbulent flow, the large eddy, they contain small eddy, the small eddy contain the smallest eddy, like that. So in that picture, if I map this thing into a particular grid size or my mesh size, what will happen? The eddy size that is above more than the size of the grid, I can able to capture those things. Those who are below the size of the grid, I cannot able to capture those things. Those eddies are called what? Subgrid scale model, right? So this eddy, I am able to capture this as it is a laminar flow. We are capturing the geometry. We will provide the necessary grid resolution to capture this large eddies, right? Eddies small than our grid size, we are not going to capture those. Anyway, just like Rand's modeling, we model those eddies to see their effect manifested in the bulk scale in the Navier-Stokes equation. Here, the smallest scale eddy, they'll influence the large scale motion, right? Through what? Through subgrid scale stress, right? So this kind of modeling is called large eddy simulation. So now we'll go details to the large eddy simulation. Now it is clear what is large eddy simulation. Yesterday in the beginning lecture, I have covered what is large eddy simulation. Now it is clear. So we are going to capture all the large eddies. We are going to neglect all the small eddies and their bulk effects, the influence of the small eddies on the large eddies or on the bulk flow, we are going to model it, right? So normally to do these things, we need to do filtration operation. So what is filtration operation? So first we need a convolution operator, right? It is a theoretical formalism, right? Above the domain, right? We need a convolution kernel. Yesterday I explained what is convolution. Yesterday I explained what is the convolution. Any multiplication in time domain or spatial domain gives the, when you do the Fourier transform, it will give a convolution in the spectral domain or Fourier domain, right? So convolution is a kind of smoothing or averaging operator in the spectral domain, right? So we have a G is the convolution kernel, right? Any flow field variable phi, okay, we have to convolve it with the convolution kernel so that it will be filtered. So this convolution kernel is taken as a filter, right? So what will happen? So just like in the Reynolds averaging, we have decomposed the flow field variable into some average value plus some fluctuation. Here in the large eddy simulation, we have any instantaneous flow field variable phi, we decompose into two parts. One is the average value, phi bar, one is the subgrid scale value, right? The difference between LES and the difference between The Rans modeling is that the average of the fluctuation in case of the Rans, they boils down to 0. So for Rans, U prime star equals to 0. But the subgrid scale, whatever we have filter you have done, so once we did the averaging, this is the Reynolds averaging, this is normal averaging, P SGS, any fluctuation below the capture length, cutoff length, this should not equals to 0. Clear? So we have a mean component, we have a fluctuation component. In case of Reynolds averaging, average of the fluctuation component goes down to 0. But in terms of the subgrid scale, the average doesn't equal to 0, right? In a finite volume framework, what is filter? In a finite volume framework, our time step works as a temporal filter. Our grid works as a spatial filter. Means, suppose we fix the grid size, right? Any eddies more than this grid size, we are going to capture. Any eddies that have dimension less than the grid size, they are not going to capture their model. So grid is kind of filter. If eddy is less than that, pass through the filter. If it is eddy size is more than the grid size, then it has to be captured, right? So the filter length is called delta. Okay, in a three-dimensional xyz coordinate, suppose we have a dimension delta x1, delta x2, delta x3. Then the filter length is the cube root of the product of three sides. Clear? This delta is called grid filter or the filter, that is the average grid size, right? Suppose this is my computational cell. Yes, not geometric mean, delta is the cube root. This is my computational cell. This is x1, this is x2, this is x3, right? Then this is my delta x3, this is my delta x1, this is my delta x2, right? What is the volume of the cube? This is around delta x1, delta x2, delta x3. This will give the volume of the cube. If I take the cube root of the volume, this will give me some equivalent length, right? That I will call filter length or the characteristic dimension of the filter. Clear? So delta is called the filter length, right? In the convolution term, in terms of the spectral dimension, once I express it in terms of the wave vector, it should be 1 by delta, that they are related to reciprocal length. Reciprocal of the length is the wave vector, right? So 1 by delta is the reciprocal. So if what happen, normally half of the delta, whatever the delta is there, half of the delta, if it is less than that, then they allow the things to be modeled, otherwise it is 0, the convolution coordinate. Clear? Normally I capture delta for filter, consider half of the delta, 1 by delta half. If it is half of the delta, then the convolution filter is 1 by delta, otherwise it is a 0. Okay. Now this is my Navier-Stokes equation, right? If I do the averaging, okay, what will happen? This is a linear continuity equation, it is a linear, so it average things goes to 0. From this nonlinear term, this gives rise to another term, right? In terms of the Reynolds averaging, we call it Reynolds stress, right? Here what we call it? LES, it is called subgrid scale stress. Okay, if we do the Reynolds averaging, we are getting a equivalent term, right? That we call tau I as Reynolds stress, right? If we are doing Reynolds averaging, but in the LES, as we are capturing the large scale motion and allow only the small scale motion to be modeled, So we call this as subgrid scale stress. Means the size of this eddies that we are modeling, they are less of the size of the grid, computational grid, right? So similarly, if we, you can find out this relationship, you put ui equal to mean plus some SGS, and we will take the average. Once you compute it out, you will get tau ij equal to this relationship, right? Similarly, if you are doing the energy equation, right, we will get another term, that is hi or hj. This is called subgrid scale heat flux. This is subgrid scale stress. This is subgrid scale heat flux. This comes out of the filter, grid filter, right? Everything is clear or any doubt? Clear? So now the question is that we know this average quantity, we can solve this, but we don't have any information regarding this quantity. We don't have any information regarding subgrid scale heat transfer. If we want to model this thing and these things, because unless we model, this problem is open. We don't have any additional equation for this, and we can model it through LES, right? So what kind of models are available, right? Subgrid scale modeling, just like we are using Boussinesq's approximation, okay? For the RANS model, here we assume, okay, the subgrid scale stress minus the isotropic component, all the derivative component, they are proportional to the mean strain rate, and the proportionality constant is subgrid scale viscosity. There itself we are calling it eddy viscosity, right? Here in the LES we are calling it subgrid scale viscosity, right? Similarly, the turbulent heat flux is directly proportional to the mean energy temperature gradient, and the proportionality constant is the ratio of subgrid scale viscosity to subgrid scale Prandtl number, right? So someone was asking me in the morning session, what is turbulent Prandtl number? Similarly, if you are doing for RANS computation, we will get a number that is nu T by PRT. This PRT is called turbulent Prandtl number. It is not a property of the fluid, rather than it's a property of the turbulence, right? So normally value between 0.8 to 0.95 they use it. It's a constant value. Sometimes they use it around 0.951 kind of thing, this property, right? So now this term is known, mean strain rate is known, right? But we don't know subgrid scale viscosity. We have to find some mechanism that can explain subgrid scale viscosity. Now what you do, just express tau ij in terms of this number. If you put this back into the governing equation, how it looks like, okay, this term, the isotropic term, let that term be captured, mixed in the add with the pressure and give some isotropic equivalent term, okay. This is some equivalent pressure, average pressure, we'll call filter pressure. Then the remaining term, okay, they will add up and give some additional diffusion. This is my viscous diffusion, this is my turbulent diffusion because of the subgrid scale stress. Clear? Similarly, this is my thermal diffusivity, right? This is my turbulent diffusivity, okay, because of the subgrid scale heat transport. Clear? So after putting this expression back into the governing equation for tau ij, right, we will get this expression. Now here the task is to determine new SGS or subgrid scale stress. How to determine it? There are several large eddy simulation model exist to determine the subgrid scale stress. One of the initial model was given is Smraganoski and Lille model. So what this model is telling? So the Smraganoski was a climate scientist, right? So he was doing research on atmospheric science and all, for atmospheric turbulence. So he in 1970s he prescribed a model, okay, that the subgrid scale viscosity is directly proportional to the strain rate and times the some turbulence length square of some turbulent length scale, right? So what this mean strain rate, we can get it, it's a mean quantity, we can get it strain rate. So what LS is called mixing length. Just think analogy to the Prandtl mixing length theory. Now we have one more variable that is called mixing length, right? LS. And what is the value of this mixing length? Is this known? No, it's not known. The mixing length is the minimum between kappa, this is von Karman constant, time D, means it is the minimum between von Karman constant into the D, means the cell center to nearest phase center distance, that is D, otherwise CS time the grid filter dimension, right? Whichever is minimum. What is the minimum distance? Suppose, okay, I have a cell center like this, right? For this cell center, okay, if I want to calculate kappa D, which D I have to consider? If my D1 greater than D2, which D I have to consider? The shortest distance between the cell center to nearest phase. Which one is the shortest distance? D2. So my D equals to how much? Clear? The shortest distance between the cell center to the nearest wall, right? That is called D. So this is the shortest distance, this is the longest distance. So you have considered the shortest distance between the cell center to the nearest phase, that is called D. D times, okay, kappa, that is the von Karman constant. If this is minimum, then this supposed to be the mixing length, okay. If otherwise, there is a proportionality constant CS times the grid filter dimension, means D1, D2, maybe another direction D3, right? Cube root of that, whichever is small we will consider. The CS again, it's a proportionality constant, okay? The value lies between 0.1 to 0.2 based upon the situation, often 0.18 they are using. Now we know once a mesh is created, we know the delta, we know the distance from the wall, right? Then kappa is known, the von Karman constant is known, so we can calculate the LS mixing length. Unlike Prandtl mixing length, this is not much complex, we can calculate this one, right? Then once LS is known, the subgrid stress is known. Once subgrid stress is known, these equations become closed. We don't need any additional transport equation, just like what? K, epsilon, omega, we don't need those things. LS is closed, right? This is called Smraganoski-Lille model. But what the problem with this model, right? The problem with this model has the issue near wall. Close to the wall, the turbulence should be what? Damp away. Wall is a damper, it damps away the fluctuation turbulence. So in the original formulation of Smraganoski and Lille, so they don't honor for the wall effect, means the presence of solid wall, the turbulence will damp away. So finally there is a method, the CS, that we are calculating the coefficient over here, right? They are the constant, right? They don't honor for the wall, right? Whether whatever the size of the delta, they don't honor for it, original formulation. But later they found it, okay, they formulated, it's called dynamic Lille-Smraganoski condition. So they use some function that is called Van Drist function, right? Then function damps away the CS value close to the wall. So this is minus exponential function. Suppose y0 close to 0. What is this one? 1. The CS near wall equal to 1. If it is a large value, this will go to 0, it will be 1. If it is a small value, then what will it has some finite value, this value goes down, right? So this gives a big number that damps out the effective stress close to the wall. Clear? So this is the additional function they call Van Rest function, right? They are using to compute the CS value near the wall. Otherwise, CS value remains constant at the core. This grid they remains constant close to the wall. The CS value gradually damps away. They use the Van Rest function, right? So the objective of Eddy large eddy simulation is accuracy. We should with minimal approximation, right? We should simulate and get the effect. Again, the introduction of this Van Rest function, some kind of approximation they give, little bit difficulty regarding the accuracy and all, right? Then subsequently several other large eddy simulation model came into picture, just like dynamic model, well model. This is well model is wall adapting local eddy viscosity model. Okay, it was introduced in 1999 by Nicod into Drucos. Okay, so they introduced this thing. So what was the issue with the Smagorowski-Lille model? The classical Smagorowski-Lille model or Smagorowski-Lille model require artificial Van Rest damping near the wall. This is the artificial damping, right? Unless we damp it, the eddy viscosity is going to give a large value near the wall. It's supposed to boils down to 0 near the wall, right? Near the wall flow supposed to be laminar, right? So once we use Smagorowski-Lille model with Van Rest damping function, okay, that's some kind of numerical error it triggers, right? To address those issues, Nicod and the Cross, they proposed a model they call wall adapting local eddy viscosity model, or popularly known as well model, right? So this is a physical rigor. This is the derivation of the well model. So in the well model, the eddy viscosity is same, some mixing length square, but instead of the strain rate, if you compare, instead of magnitude of the strain rate, they have deviotic component, strain rate to the power 5 by 2, the deviotic component of the strain rate to the power 3 by 2, 5 by 2, right? Then this is the mean strain rate tensor SS, right? From that, what is the deviotic component? This is the deviotic component. They combined it with this is the Kronecker delta function, and they calculate the deviotic component of the strain rate, right? Then again the mixing length LS, this is the minimum of, this is von Karman constant into the minimum distance of the wall to the nearest cell center time CW into delta. Delta is the grid filter length as explained earlier. Then again CW is a constant, right? So this CW value, okay, just a second. This CW value somewhere mentioned, it's around 0.1 something. Okay, this is called well model constant. Okay, so this is again a constant, right? So now let's come. These are the data from the DNS. These are the hexagonal one is the LES simulation data. This one the LES simulation data. The circular one the well model simulation data, and this is the U plus versus the Y plus data from the DNS, right? So what we observe that the Smagorowski-Lille model with the use of Van Rest damping function, they give the deviation from the DNS data, right? While the well model, they ideally gives identical information or velocity distribution compared to the DNS data. So this model is relatively this model is relatively more accurate compared to the Frank-Onoski-Lil model with the Van der damping function. Then these things, the LES things, it seems quite relatively easy compared to the RANs, right? But why it is so difficult? Any idea? The computation, we have a minimal approximation. In the RANs, we have a lot of approximation. The third order, the correlation coefficient, those correlation coefficient were assumed in terms of the equivalent diffusion. We have a closure coefficient. We from experimental finding we fix those closure coefficient, calibrated those. But here the idea is the minimum is the approximation, the accurate is the model. Maximum is the approximation, the model is less accurate. Minimum is the approximation, more accurate is the model. But if LES, the formulation seems relatively simple compared to them, but what is the complexity? The complexity is the intensive computational requirement. The amount of grid size that you need for the RANs computation, if you are doing LES, maybe you need 20 times, 30 times more grid structure in the LES. Okay, I will show you. During my tenure in the lab in Po, I did some intensive LES computation. So we did on different type of mesh. This is called tet mesh, triangular mesh. Okay, on the surface, and there is a prism layer we did in the just like low Reynolds number without any modeling for the wall. We solve the LES, right? So from the wall we integrate up to the core. This is a hexagonal at the core, triangular mesh at the center, sorry, surface. The other one is a rectangular mesh at the surface, and at the core it is hexagonal also. These are the different, what you call, mesh structure. Their effect I evaluated and match with the experimental finding of our group. So this is how my LES data match with my experimental data. 2022, with this experiment of that for some natural convection in a cavity, annulus cavity, we did the experiment, okay, and matched our experimental result. This is our in-house experimental result with the LES data, right? This is the mesh 1 and mesh 2, different kind of mesh. We tested, we test this mesh, we test this mesh, different kind of mesh structure we test. Then this was computed using the Code Saturn. Yesterday I was talking, right? Code Saturn is a open source CFD software made by EDF, that is the electricity distribution company of the France. They made it open, okay? With that EDF software, we did this computation, right? So we found the solver itself is capable of considering different kind of mesh structure to produce identical result, right? So the mesh structure, the type of meshing has minimal effect, but what is the real thing? So now we did computation with the mesh structure of 3 different sizes, right? One is 16 million, one is 24 million, one is 34 million. Okay, we found the 16 million mesh somehow underestimate the experimental result. The 16 million mesh somehow underestimate the experimental result, right? We did not find the good match. While we increase the mesh count to 24 and 34 million, then we found they are producing accurate result. So if I do it in the RANs, maybe I need 2 million mesh for the geometry. If I am doing LES, 16 million mesh is not getting sufficient. These are run in 2000 parallel core processor. In the Jena cluster, this program was run in 2000 parallel core processor almost for 3 weeks of time to get a convergent result. Okay, so that much of intensive and expensive is the computation. Okay, but it is possible. Some other LES we did it. Yesterday I have shown the flow across a cylinder. Yesterday I was showing, I have done the LES simulation. So it based upon what is the Rayleigh number and all. Here almost the Rayleigh number was 10 to the power 9 something. Okay. This was done in the Jena cluster, that is the French national mission supercomputer. It's presented somewhere in the Paris. So in that supercomputer we did it. Okay. Almost for 3 weeks the computation last, and we are getting that even if 16 million mesh was not sufficient to reproduce the result. Annular cavity, it's relatively simple, not much complex, but it's a big size, some meter, in order of some meter, the dimension of the geometry. Uh, in the dimensional form we solve it. You can non-dimensionalize it, but in the dimension form we solve it. Doesn't matter. Even if non-dimensional you bring it one, you have to accordingly you again break the mesh size. So we found the 24 and 34 million mesh, they give the identical result while 16 million was underestimating, right? So this much of intensive calculation, computational requirement is more, right? That's why the LES is still bit not usual thing for industrial practice. For simple geometry, yes, flow across a cylinder, flow, natural flow in a cavity, those things we can do it. But imagine an industrial pump, blower, turbine, we are doing it. How much things we need it, computational requirement will be, right? So this is the thing. So now let's move to the next. Okay, then there is a indicator called LES IQ. This is the LES quality indicator, right? There is no grid independence test in the LES. You go on doing the resolving your grid size, you will finally reach at DNS. There is no grid independence test, just like RANs you are doing for LES. If you go on splitting your grid or making your grid small and small and small, gradually reach at DNS. So there is a criteria they call LES IQ, LES indicator, that is defined at 1 plus 0.05. This new is the laminar viscosity or kinematic viscosity times subgrid scale viscosity divided to the power 0.53. Okay, this you have to average for a long time. You have to do the averaging, right? If you find it, if it is more than 0.8, your results are good. LES results are reliable. If it is around 0.95, your LES results are close to the DNS result, or this is called quasi DNS. If it is 0.98 around, then this is the DNS. Your LES is giving equivalent to the DNS result. What we found, whatever our mesh size around, when we reach at the mesh size around 35 million, our results become close to the quasi DNS result. That's why once you are into the DNS level mesh, then the subgrid scale model you will find hardly they are affecting. Whether you are doing well or Smaganovsky well, their effect you will find only in the small mesh, sorry, a large grid size. Once your mesh is sufficiently resolved, so you will not get any difference between them. So you can see we did in well model, dynamic, this Smaganovsky and Lil model. This is dynamic model. 3 model we did it. Okay, 3 LES model, and we compare with the experiment. We found all the 3 models are reproduce the identical result, because my mesh size 35 million was sufficiently resolved, right? So it is kind of DNS computation, means we are capturing almost all smallest size eddy that can be possible in the domain. So almost we are capturing some spectrum up to here. We are neglecting very small portion of the thing, right? So this was all about LES. This was all about LES. Okay, large eddy simulation. So yes, there are a lot of mathematics, there are a lot of other stuff regarding LES, averaging, mathematical stuff. So this itself is a 1 semester course. Just within 30-40 minutes I cover the cream of it. There is a book by Perry Sogot, French author. Okay, if you go through the book, you will find there is a whole semester course on large eddy simulation. Several kind of averaging. Just we are doing Reynolds averaging. There are several kind of averaging. There are several kind of filter design. You have a rectangular grid, the filter design. You have a polygonal grid, there is a filter design. There are different kind of convolution kernel, and some people, this LES we did on a physical space, x, y, z coordinate. Some people they do LES on spectral space. They transfer the equation to the spectral plane. They do the spectral LES. Okay, they do the Chebyshev algorithm. They do the spectral LES. Professor Rajaram, he was doing LES for some, yesterday was discussing from some geophysical flow, but that not in physical space. They transform the Navier-Stokes equation into the spectral plane and solve it. They are solving the convolution operator, interaction among eddy in the spectral space, right? And some other professor like Professor Tapan Sengupta from IIT Kanpur, they solve the implicit LES. They don't explicitly assume any subgrid scale model, right? They are using very higher order, fourth order or sixth order numerical scheme, right? They are very much accurate, just like we are using for DNS. They are explicitly taking care of the LES. They call it implicit LES. But again, designing those numerical scheme in the commercial solver or open source solver, it's a too challenging task. Maybe they can customize it for a particular geometry, channel or forward backward facing step, etc. Making a generic LES solver was quite difficult. Those are called implicit LES. This is subgrid scale LES. Okay, these are openly available in the open source software as well as paid software like ANSYS, Fluent, Star CCM, OpenFOAM, Code Saturn, etc. The important thing in LES simulation, so the numerical scheme need to be very much accurate, right? So in the RAM simulation, everyone using upwinding. How many of people of you know upwinding scheme? You know what is the meaning of upwinding? What is the meaning of upwinding? Okay, okay, I will give some short introduction to CFD. Okay, the scheme, although this is not a CFD class, but okay, it's good to see, good to give some example. Okay, this side there is a ice cube. Okay, this side there is some fire. Okay, at the center the person is standing. It's in the midway. This is L by 2. This is L by 2. Okay, this is my ice cube. Okay, this is my fire, right? So at the mid, the person is standing. What he will feel? He will feel hot, he will feel cold, what he will feel? At the center, at the middle between the two, the person is standing. What he will feel like? Hot or cold? If there is not any external flow, he will feel influence of both ice and air, sorry, fire, right? All of a sudden what will happen? Someone put some fan or blower this side, so the cold breeze started or cold wind started to flow. Now what will flow? Cold or hot? Relatively cold, right? Similarly, if someone put some other blower over here, that blower is switched up. Now hot air is coming this side. Although ice is there, it will feel hot, right? So the same concept, when there is not any additional velocity in the diffusion, when you do the grid, the center grid feel the influence of this grid, and north, sorry, this way is the east. This is the west. This is the center grid. Okay. The center grid feels the influence of the east grid and west grid. But if there is a strong advection current, what will happen? The direction it has the advection current, it has to be respect that one. So giving the respect to those direction having advection current, this is called upwinding. We are using some scheme that gives respect to the direction of the flow, right? So what happens in the normal laminar simulation or RAN simulation, we are using some kind of upwinding scheme. There are different upwinding scheme, first order or upwind, second order upwind, this is a third order muscle scheme, quick quadratic upwinding, different kind of upwinding scheme you might have known or studied in the CFD, right? But the issue of with the accurate one is the central difference scheme. The most accurate is the central difference scheme. But the issue is the central difference scheme is that this is susceptible to numerical stability. The result is less stable. Once you do the central differencing instead of upwinding, the result will not be numerically stable, right? Because you don't respect the direction of the flow, right? While we are doing LES simulation, we cannot do upwinding because we want as much as possible accurate solution. We cannot force a particular directional preference on a grid to computation. So to do that, they are using a method called bounded central difference scheme. If you give the only central difference scheme, that is numerically unstable, upwinding is not accepted. So they some kind of boundary flux limiter on boundingness they put on the central difference scheme, and for spatial discretization of the momentum equation, bounded central order difference is preferred for the LES simulation. Similarly, second order bounded time discretization we used for the LES simulation. Yes, at least it is second order or higher order, right? Bounded second order scheme you are using for discretization of the space. Also the bounded second order implicit scheme we are using for the time matching. Then only our results are accurate, right? So I will show how pressure and velocity are coupled. Normally in the ANSYS fluent they recommend use the standard or second order for pressure discretization. Don't use Pestro scheme, right? Use simple C for the pressure velocity coupling, right? There are certain criteria, then there is certain flux limiter. Okay, we will see all those things while going through the hands-on training today LES session, right? We will see such things, right? So doing LES is relatively simple operation seems like, but it has a lot of challenges, right? So what are the challenges? First, we need a very good mesh. Second, we need very accurate numerical schemes. Then only our LES results are reliable. Based upon the geometry, if there is some source or something happening in a particular region, suppose flow across a cylinder in the throughout the wake region, why you need a fine mesh? You need where the flow reversal occurring or vortex shading occurring. In the free stream region, we don't need such fine mesh, that you need to capture the vortex shading in the region, just in the wake region, right? So again, it's based upon the experience of the user. It's a heuristic approach. You need to decide judicious about where to use the fine grade, where to use the coarse grade. But yeah, definitely yes, The course grid DNS you can tell it, but again your grid need to be sufficiently resolved to capture those eddies, right? So that's why first what we do in the sufficient fine mesh, first we do the RANS simulation. The RANS result somehow we feed as an initial guess to the LES to reduce the computation time. Sometimes starting the results from the zero takes a lot of time. Initially we do a RANS. The RANS result we sometimes use the velocity field and pressure field as an initial condition to perform LES. Right? So there are a lot of other computational stuff is there. Once you do the LES, so result post processing, you can see there is a lot of things called cube criterion, this lambda criterion to visualize the vortex structure, etc. You can see the small scale eddy movement. All those things we can see it today on hands-on training, right? This will give you the information on the flow transition. If there is a laminar flow, then the flow is undergoing transition, then the flow become turbulent. We can see it from the visualization of the streak line, the burst of the streak line. All those things give a very fascinating, very interesting subject, provided you give it sufficient time. You get very interactive things. You might have seen some video, the vortex structure around the Boeing, someone put in YouTube or LinkedIn, a lot of vortex setting across the Boeing aeroplane and all, right? So this is all about the theoretical definition and the formulation of large eddy simulation. Although it appears simple, but still the computational implementation is quite challenging. Making the scheme working, giving the stable result, that is also quite challenging and depends upon the experience of the user. And the most challenging job is to find a good mesh. Okay, you cannot have the mesh that is sometimes non-conformal interface, so that interpolation error will be there. So you need to minimize your grid error due to grid size, error due to your numerical discretization or numerical scheme, error due to if any interface is there or non-conformal interface is there. If you minimize all sorts of error, then your results will be as much reliable as possible. Otherwise, the beginning I told you what is the hallmark of a chaos. Slight perturbation in the initial condition gives you completely different result, right? Even if you're doing LES, even if you're doing DNS, here you see the for nonlinear equation, very small perturbation, very small change in initial condition, they can give a large deviation or chaotic result, right? And this perturbation may be introduced due to the grid, large grid, they may be the due to the improper numerical scheme. If the numerical scheme is not sufficiently accurate enough, there may be some error during the numerical truncation, right? Those small error may give you some false result instead of the true result, right? So you need to be judicious, you need to be little bit experienced, and you need to spend time to know what exactly you are doing, whether your grid is sufficiently resolved, your numerical schemes are sufficiently fine, and you are doing everything correct. So with this lecture, we have come to the end of this session on turbulence modeling. Okay, the end of the day, we have another 2 hours we'll spend on LES, hands-on training on LES modeling. RANS will do the flow across the cylinder with K epsilon, K omega, LES. Although I am not sure, we can run it in the laptop, or we need a cluster. If you have a cluster access, you can run it. You can compare the result. And who is taking your CFD classes? Who is faculty? You can, maybe I will ask Somnath sir. He can check the results. You can share it with your results. How accurate? Okay. Or you can directly share it with me. Not the file, the result. different RANS model, you run the problem, find the results, you share the result for different RANS model, LES model, comparison. You can share it with me. If it is part of your examination process, those who are auditing or crediting some course, this seminar is part of some course, then we have to do some exercises, right? So today, maybe after 10 minutes break, we'll meet again in the seminar room. We'll start hands-on training. Okay? If you have any doubt, please. If you have any doubt on LES, please. Yes, this is definitely the filter length, how the filtration is done. The developer has defined some criteria to do the filtration, averaging operator, right? Definitely that different for the quad mesh to the triangular mesh or prism shape mesh or the poly shape mesh, okay? But they are implemented such nice way in the code section, we did not get any difference. Maybe different solver have some different implementation criteria. Maybe in open form, maybe in ANSYS, maybe in CCM, different mesh structure maybe give you different result. So last time when I was discussing with the developer ANSYS, they too find, so this has very minimum effect. No, time step has influence. Time step has influence. You should try to put your time step such a way that the Eddy has a turnover time, right? You are trying to capture the movement of the small Eddy, right? You should have a time step that should be less than the turnover time of the Eddy. If you take a small length scale, large time scale, then the Eddy is, do you think you can capture the small Eddy? No. You should have a nominal time scale also. It's, yes, there is not any straight cut answer. Everything depends upon your Reynolds number, Rayleigh number, problem definition, right? So again, the problem with LES is getting a converge statistics, right? Converge result. So what converge result? So you will get the Reynolds stress, okay? You will get a turbulence stress. Yes. These are the average quantity, right? These are the average quantity, right? What will happen during the run time? You can have take product of two velocity component u1 u2, right? You can take, then once you product of two component, then you can take the average, time average of those things. Then you can take average of individual component. If you subtract your the product of average of product of two things and product of two individual average, this will give you this tau ij. At some particular location or particular point, you need to put some probe or monitor this statistics, right? This needs to be sufficiently converge. It takes a long time to converge, means there is a little bit change is there. This convergence takes a long time to do the thing. That's why LES simulation normally spans over weeks of time. Small time step, computation takes sufficiently time to get a independent result or the converged result. So, yes, any other question? Any other doubts? Yes. So, the only way to find the mesh independent solution to run in that mesh, run in a finer mesh and compare the result. There is no any alternate way. So, any more question on LES? If no question, then we come to the end of this session. Then thank you everyone for your patience, for your attention. So it was a pleasure for me. Last 2 days I enjoyed teaching at IIT Kharagpur, interacting with the young and dynamic minds of the nation. Okay, I hope whatever I taught in last 2 days in the classroom, they will be interesting for you. This will helpful for you in your future research or your future academic purpose. Some of you maybe do research on the turbulence in. I wish I to see some of you, some of the faces from the bench as a leading researcher of the turbulence in future. So I wish you all the best. Again, thank you. Okay. After a 10 minutes break, 15 minutes break, let's see in the seminar room.